Now we are like, you can start.
Yeah, we are very happy to have Nikhil Mande, former student. When he left TIFR, his passion was blindfolded Rubik's cube solving. He was famous for that. Now it seems he's becoming famous for quantum stuff.
Thanks, Adversary. Thank you everybody for attending here and online. So I'll be talking about some very recent work, in fact, that I did with two wonderful students, PhD students from Amsterdam. We put it out on archive only a month ago, and feel free to interrupt me with questions. I'm happy to take questions at any point of time. Okay, so here's the sketch of the talk. So initially, I'll tell you, I'll try to motivate and define this query complexity, this query model of computing Boolean functions. And during this part, I hope to convince you that there's a one-to-one correspondence between query algorithms and decision trees. So the query complexity of a Boolean function is equal to the depth of the corresponding decision tree. I hope to convince you of this fact. If you've already seen it, then you'll know it's a simple fact. And then in the second part of the talk, I'll talk about another natural measure of decision trees, which is rank and randomized rank. And then we'll shift gears a little bit. And in the third part, we'll see that if you have a classical query algorithm computing a Boolean function, and if it has certain nice properties, in the sense that if the decision tree corresponding to this query algorithm looks nice, then you can obtain a quantum query algorithm, which has some speed up over the initial classical query algorithm. And then I'll end with the summary. Okay, though most of you may not need it, here's some motivation about why one should study complexity theory. So one of the most famous open questions in maybe mathematics and the whole of computer science is the P versus NP question. In layman's terms, this asks, can efficiently verifiable problems also be efficiently solved? So the class NP somehow captures the class of efficiently verifiable problems, and the class P is the class of efficiently solvable problems. And we expect that this is not the case, but in a sense that can be formalized, in several senses that can be formalized, we're nowhere near the resolution of this question. So just as an example, think of this famous Sudoku puzzle. So if I give you a Sudoku puzzle and it's not completed, it's partially solved, and I ask you, does there exist a solution to this? This is potentially hard to do, to compute, to find out if there is a solution. On the other hand, if I give you a solved Sudoku and say, please verify for me that this is a solution, that's fairly easy to do. It's just a local set of constraints you need to check and so on. And so Sudoku, if defined correctly, is a canonical example of an NP problem. So this this notion that I told you that we expect this not to be equal is captured very nicely in this meme that I'm very proud to have created. So how do we tackle such problems? It's one natural approach that's been studied for the past couple of decades maybe is let's tackle analogous questions in simpler models of computation where we know how to prove such separations, P versus NP type separations, and hope that these separations in these simpler models of computation actually give us some insight. If people don't mind, I'll take off my mask. With the hope of gaining understanding towards the original problem itself. Okay, so here one such model of computation is the query model of computation, query complexity, and here's how this model works. So in this setting, you have a known n-bit Boolean function f. So it takes as input an n-bit string and outputs a single bit value in 0, 1. And there's an unknown input x, which is an n-bit string. And as you can probably guess, the task is to compute f of x. And what are you allowed to do? You're allowed to query bits of x. So for example, you can say, what is the value of x5? And then that will be revealed to you. And the cost of such an algorithm, a query algorithm, is just the number of queries made to X. So we're abstracting out all of the internal computations that are independent of X, which you would usually consider in, for example, the classical Turing machine model. And the cost is just simply the number of accesses to the input you're doing. And the query complexity of F is the cost of a best algorithm computing F. So in the worst case here means overall worst case over inputs X. So if you didn't follow this, here's a small example capturing what a query algorithm looks like. So consider the OR function on n bits, which takes an n bit input and outputs 1 if and only if there exists at least one 1 in the input. So initially, to start with, you have an unknown n bit string, and suppose you have an algorithm. This algorithm dictates you to query this bit, and let's say that bit is revealed to be 0. Now suppose because the answer is 0, the algorithm dictates you to query this bit here. This is revealed to be 0, and then you carry on until you hit a 1. And now at this point, you don't need to make any more queries because you know that the function value is 1. No matter what the other question marks are, this input is going to evaluate to 1 because of the definition of the OR function. But as you can guess, and you can formally prove it, that no matter what algorithm you have for computing OR, there's always going to be one input, in some sense a hard input, for which you need to make all of the queries. You need to query all of the bits in order to output the correct answer on that. So in other words, the query complexity of OR is n. And in the query setting, easiness is typically polylogarithmic in the input size, and hardness is like polynomially large. So the OR function is hard in the query setting. It's maximally hard. So the query complexity of any function is at most n. You just query all of the input bits, and whatever you do after that is not charged. Okay. So why study query complexity? There's multiple motivations from the algorithmic side and complexity theoretic side as well. So from the complexity theoretic side, we can prove unconditional lower bounds. As I just sketched, the query complexity of OR is maximal. Moreover, separations in query models here. So there are natural analogs of classes like P and NP and so on and so forth in the query setting. And it's known, for example, in the query setting that P not equals NP. And such a separation translates immediately to oracular separations for the corresponding Turing machine complexity classes. And from the algorithmic side of things, this is more from a quantum query algorithm perspective. So most important algorithms are naturally phrased as query algorithms. And just as examples, Shor's period finding and the Grover search algorithm, this period finding and search have natural formulations as quantum query algorithms. Okay. Now let's get on to this bold claim that I made on the first slide, that query algorithms have a one-to-one correspondence with decision trees. So to recap, you have this known function f and unknown input x, and your goal is to compute f of x. And the cost you're charged is the number of accesses to bits of x. So let's look at this model of computation, which is a deterministic decision trees. A deterministic decision tree is depicted here, an example. So internal nodes are going to be labeled by bits. Edges are going to be labeled by zeros and ones. So each internal node has two outputs, 1 0 and 1 1. And then leaves are going to be labeled by values in 0 1. So how does a decision tree compute a Boolean function? It's in the natural way. So if the first bit is a 0, you go down the left path. If it was 1, you go down the right path, and continue so on until you hit a leaf. And when you hit a leaf, you output the value at that leaf. Okay. So this decision tree computes a Boolean function described here. Now, moreover, this also captures a query algorithm that computes this function. So the corresponding query algorithm would first ask, what is the value of x1? If the value is 0, you would go down the left subtree. If the value is 1, you would go down the right subtree until you hit a leaf. What is the query complexity? The query complexity is the maximum number of inputs the query complexity of this algorithm or this decision tree is the maximum number of bits you need to query. And what is that? It's nothing but the depth of this decision tree. And it's fairly easy to see that there's no unique decision tree that computes a Boolean function f. So if you minimize overall the depth of all overall decision trees computing f, this is defined to be the deterministic query complexity or deterministic decision tree complexity of f. There is a natural generalization to randomized query complexity as well. I'll describe this in a little more detail later. There also is a generalization to quantum query complexity. I'll not get into too many details, but the most important part to take away how it's a generalization of classical query algorithms is that you can make these queries to the input bits in superposition. That's one of the most important generalizations. So over here, this Z register captures workspace. The I register captures which input bit you're querying, and the second register over here captures the output of that query. How does a quantum query algorithm look? You start in a predetermined start state, which is independent of the input, and you apply a sequence of unitaries, U1 through UT, interspersed with these Oracle applications, where these UIs are independent of the input. And at the end of this process, you perform a 2-outcome measurement on a designated output qubit, and you answer output the value observed. It's fine if you don't completely follow this. I mean, most of the quantumness in this talk will use some classical tools and convert it to a classical problem later. So the correctness requirement of a quantum query algorithm is that for all x, for all inputs x, the probability that the output of the circuit on x equals f of x is at least 2/3. And again, the cost is the number of accesses to the input, which in this case is the number of Oracle calls, which is number of applications of OX. Again, the quantum query complexity of a function is the minimum cost of a quantum query algorithm that computes in this sense. Okay, so here's some query complexity of some well-known functions, and I apologize for not putting references and citations. I didn't want to fill the screen, but I'll be happy to tell you all the references later. So for the OR function, which outputs 1 if and only if at least one of its input bits is 1, the deterministic and randomized query complexities are maximal, and the quantum query complexity is theta of square root of n. So there's a quadratic saving to be had here. For the parity function, so the parity function is one where you take an n-bit input string and the output is 1 if and only if an odd number of the inputs are 1. So the deterministic and randomized query complexities of this are maximal, like truly maximal. But the quantum query complexity is you get a saving of a factor of 2 here. And for this function, which is a complete binary and or tree of size n, I'll formally define this function in later on in the talk. But for now, let's just call this function f. So for this function, randomized query algorithms are strictly better than classical query algorithms, and quantum query algorithms are strictly better than randomized query. So this function will play an important role later in the talk. Okay, so were there any questions about this section?
So these are all one-shot results, right? So there will be sequential analog of this.
These, as in these query algorithms and all, are all sequential.
No, I mean like say, I'm giving instead of giving one string, I'm giving you like say k different strings, and you have to make cases for all these k different strings, each of in length.
I see. So there are like direct sum and direct product results. I don't know if these are the sort of results you're talking about. So typically in these sort of query settings, these are known. Like if you have to compute the outputs correctly of, for example, of each of these k instances, then you require you're required to do at least k times the amount of computation it's done for a single instant. So such statements are known in certain settings, but that's nowhere near the focus of this. Yeah, but it's a nice question. Yeah. Any other questions? Okay, so I hope at least I convinced you that classical query algorithms have a one-to-one correspondence with decision trees, and the cost of a query algorithm is the depth of the analogous decision tree. And now let's talk about this other measure, rank of decision trees. First, I want to tell you about this notion called guessing complexity. It wasn't defined to be such in these papers, but we invented this notation, and I'll tell you why. So it was introduced in by Lin and Lin in 2016 and Beigi and Taghavi in 2020. So they used this notion to prove quantum query upper bounds of quantum query complexity upper bounds for Boolean functions. So guessing complexity is a measure of a decision tree. So what they showed is that if you have a classical query algorithm in the form of a decision tree, and its guessing complexity, whatever it is, I'll describe it now, happens to be small, then you can extract from this a quantum query algorithm that has a speed up over the initial classical query. So what is guessing complexity of a decision tree? Let's take a decision tree or a query algorithm, and for now let's just ignore all of the labels at the vertices, the edges, and the leaves. And I give you a task. The task is the following: assign a coloring to the edges of the tree using two colors, blue and red, such that every internal vertex has one outgoing blue edge and one outgoing red edge. And what you want to optimize is the following: you want to say that for every root to leaf path, so whenever I refer to a path, I'm going to mean a root to leaf path. For every path, the number of red edges on that path is small. So the maximum number of red edges on a path is what you want to minimize. So for example, in this setting, you can see that this coloring that I've assigned is consistent with this first requirement that every internal node has one outgoing blue and one outgoing red edge. And let's look at, for example, this root to leaf path has two red edges. Similarly, if you go over any other root to leaf path, you'll find that it has at most two red edges.
Same as what Shandik and Bruno defined as the zero complexity or something.
Not quite, because these red edges could have been on this side.
Oh.
So it does turn out to be equal to another notion. It's a spoiler, but I'll tell you on the next slide. Yeah.
So this is not really only because the graph is not complete.
Yes, yes, you're correct. If you had the complete binary tree, you can show that the guessing complexity would be exactly equal to the depth. Yeah. So because every node you're going to have one outgoing red edge, you just keep following all the red edges. You will get there always, no matter what coloring you have, there exists a path of red. So yeah, in this case, the complexity of this coloring that I assigned is at most is 2, and you can show that there exists no assignment, no coloring assignment that achieves guessing complexity 1. So the guessing complexity of this tree is 2. Why have I called it guessing complexity? I haven't told you. So you can think of guessing complexity as an additional procedure over a decision tree. So this, now let's go. Imagine that these vertices are again labeled just as in a decision tree, and so are the edges. So along with the decision tree process itself, you're also executing a guessing scheme. In the sense that before making this query, you guess what the output is going to be. So you guess that the output is going to be the blue edge. So let's say the variable queried here was x1. Before querying x1, I'm going to guess that the output of x1 is 0. Let's suppose that the outcome came to be 1. So I've made a wrong guess. So a red edge corresponds to a wrong guess. Now at this point, I'm going to guess that the value of this variable is the right one. And if the value is actually this, I've made another wrong guess. So the guessing complexity exactly captures the number of wrong guesses made, the maximum number of wrong guesses made given a classical variable. Okay. If you're not happy with this definition, let me tell you about an equivalent definition. So guessing complexity, again, it was introduced in the context of proving quantum query upper bounds in terms of classical query complexity. There's this notion of rank, which was introduced by Ehrenfeld and Hausler in '89 in the context of learning theory. And rank is defined in a recursive manner. So it's again a measure of decision trees. For a decision tree that's a single leaf, its rank is defined to be 0. And recursively, you say that the rank of an internal vertex is depends on the rank of its children, as given by this these cases here. If the ranks of its children are equal, then add 1 and assign that to be the rank of the parent. And if they're unequal, then assign the maximum to be the rank of the parent. So, and yeah, the rank of the tree itself is the rank of the root. So just as an example, let's see. This is the same tree, maybe stretched a bit from the previous slide. So the rank of all leaves is assigned to be 0 as per this definition here. Let's look at this node here. Since the ranks of its children are equal, then add 1 and assign it to be this. So the second case applies. So the rank of this node here is 1. Same thing here. Same thing here. But if you look at the rank of this node, one of its children has rank 0, the other of its children has rank 2. So the first case is going to apply. So the rank of this node is 2. And the rank of the whole tree in this case is 2. So what we show, and it's not very hard to show in fact, is that for any given decision tree T, its guessing complexity equals its rank. And this answers an open question of Lin and Lin, who explicitly asked if this guessing complexity equals any combinatorial measure of Boolean functions that's studied in the classical literature. And yes, it equals rank. So since the proof is so simple, I just want to try to sketch some of it on this slide, or maybe prove it on this slide. So the proof strategy is as following. We're going to show that guessing complexity can be defined recursively. So the guessing complexity of a tree that's a single node is 0 by definition. And otherwise, we're going to show that the recurrence that this follows is exactly the same as the recurrence that rank follows. So they're syntactically the same object. That's how the proof is going to go. As a proof by picture. So we have to show greater than equal to and less than equal to. Let me just sketch this second one, less than equal to. So guessing complexity involved an assignment of colors to edges, just to quickly recap. So let's suppose now that the guessing complexity of the right subtree is strictly larger than the guessing complexity of the left subtree. So suppose the right tree's complexity is B and the left tree's complexity is A, where A is strictly less than B, suppose. Now consider two colorings of these trees. Consider colorings of the left tree and the right tree that achieve this guessing complexity, in the sense that for all root to leaf paths here, there are at most A red edges, and for all root to leaf paths here, there are at most B red edges. And now I'm going to retain these two colorings and construct a coloring for the whole tree, where the left, the root to its left edge is going to be colored red and the other one blue. And now let's look at what guessing complexity this achieves, what this coloring achieves. So any root to leaf path in this subtree is going to continue to have at most B red edges. But in the left side, it's going to have at most A plus 1 red edges. But since A was strictly less than B, it means it's going to have at most B red edges. a plus 1 is less than or equal to b. So that shows this GT is less than or equal to this maximum. This one is fairly easy to show as well, and this greater than or equal to inequality follows in a fairly straightforward manner as well. So if you weren't happy with the definition of guessing complexity, then here's the rank. If you're not happy with this, here's another definition. This characterization is due to Kudlak and Impagliazzo, and this has been used in proof complexity. So what I want to get across is that this notion of rank is a very versatile measure. It's been used quite a lot in different areas. So this in this setting, there's two players, a prover and a delayer. Again, there's a known function f and there's an unknown input x. And informally speaking, the prover's goal is to force f to become a constant function, and the delayer's goal is to score as many points as possible, which I'll try to define now. So in the beginning, you start with an unknown input, and let's say the underlying function is OR on 3 inputs. So the game proceeds in rounds. The prover is allowed to query a variable to the delayer. So the prover can ask, for example, what is the value of x1? And now the delayer has three options: either say x1 equal to 0, or x1 equal to 1, or defer the choice to the prover. So they say you choose. And in the case where they ask the prover to choose, the prover scores a point. The delayer scores a point. So let's just suppose hypothetically that the delayers ask the prover you choose. So the prover could potentially choose the value 1 here, and that forces f to be a constant. That means no matter what the other bits are, this function is a constant since the first bit is equal to 1. So in this case, the delayer would score a single point because they only asked the prover to choose once before the prover could force f to be a constant. So let's say the delayer says, okay, x1 equals 0. And the prover says, what's the value of x3? x3 equals 0. What's the value of x2? Now at this point, the delayer has nothing to lose and they want to score a point. So they say, you choose. And regardless of what they choose, the function value is fixed. So no matter what the prover strategy is, the best delayer strategy over all prover strategies is equal to 1 in this case. You can show it. So the rank using this prover delayer, the maximum number of points that the delayer can score is 1 for the OR function. And in general, the maximum, if you had for any other Boolean function f, the maximum number of points that the delayer can score is exactly the rank of f. And maybe I didn't mention it earlier, the rank of f is the minimum rank of a decision tree that computes f. So now there's a natural generalization of classical query complexity or deterministic decision trees to randomized query complexity.
So there are, are there examples of decision, like for instance, if the goal was to minimize the rank, the best decision tree could be different compared to the goal being to minimize query complexity. Right? It's not that the best rank is you take the best query complexity and on that you assign a color.
That's true. Off the top of my head, I don't have examples, but I suspect that they are different things in the sense that you need not look at the best query algorithm and look at the rank of them. I'll need to think about it. Okay, so here's a generalization to randomized rank. How does a randomized decision tree look? It's so a randomized decision tree computing a n-bit Boolean function. I want to take the view today that it's a distribution over deterministic decision trees, such that if you sample a deterministic decision tree from this, according to this distribution, and evaluate t of x, evaluate that decision tree on the unknown input, then the probability that t of x equals f of x is at least 2/3. And what's the cost of this randomized decision tree? It's the maximum depth of a deterministic decision tree in the support of this. This is a standard definition. Analogously, we can also define randomized rank, which is simply the maximum of rank of a decision tree in its support. So the randomized rank of a Boolean function f is the minimum rank of a randomized decision tree that computes it, or the minimum randomized rank of a randomized decision tree that computes f in this sense. And now questions of the form deterministic query complexity versus randomized query complexity have been studied to quite some extent. And in this slide, I'll tell you about what happens if you ask the analogous questions for rank and randomized rank. So it's fairly easy to show that the rank of a tree is at most its depth. And similarly, the randomized rank of a tree is at most the randomized depth. This is fairly straightforward. And now let's suppose you can ask the question, do there exist functions for which randomized rank is much smaller than deterministic rank? And if you allow for partial functions, then if you consider the approximate majority function, which is defined as follows, you have an n-bit string, output 1 if the Hamming weight of the input or the number of ones in the input is larger than 2n by 3. Output 0 if the number of ones in the input is less than n by 3. So this function has randomized query complexity order 1. So that implies by this statement here that it has randomized rank order 1. As for showing a rank lower bound on this, a deterministic rank lower bound, you can show it, for example, using this characterization of proof-or-delay again. So you can show that the deterministic rank of approximate majority is omega n. So rank and randomized rank can be maximally separated for partial Boolean functions. What about total Boolean functions? So a partial Boolean function is one that is not necessarily defined on all the inputs.
We use it by query.
Sorry?
Is it used by query?
Well, the query algorithm knows that the function is partial. So
We are considering the function which is partial. We are talking about that function is rank.
yes, yeah. So again,
Rank is defined only for tree, not for function.
sorry.
Rank is defined for trees, right?
Yeah, but then if you want to talk about rank of a function, you just minimize overall trees computing the function.
So basically on the set of strings on which the function is not defined, you don't care what the query algorithm.
Exactly. So you still talk about trees. So partial functions still have query algorithms for partial functions still look like trees. It's yeah. So what about total functions? So we know, for example, that deterministic query complexity and randomized query complexity are polynomially related for all total functions. Is such a thing true for rank versus randomized rank? We don't know. So here is an approach to show at least a polynomial separation between deterministic rank and randomized rank. Let's look at a function that witnesses separation, a polynomial separation between deterministic and randomized query complexity. And then let's just somehow hope that the deterministic rank is actually close to the deterministic query complexity. Now, since the randomized rank is at most randomized depth, this would imply that randomized rank is polynomially smaller than the deterministic query complexity. This is, I hope, it's a natural approach. So we tried this for functions that are that maximally separate deterministic and randomized query complexity, and it turns out that this second bullet no longer holds true. So, for example, for this pointer jumping functions, one of these papers was done at PIFR. These references are from the journal versions of the paper. The initial versions are from 2015 when they came out on Arctic. So it turns out that for these pointer jumping functions and their variants that witness a maximal polynomial separation between deterministic and randomized query complexity, it so happens that the rank of these functions is much smaller than the deterministic query. So this approach breaks down. So what do? We look at another function that witnesses a separation between deterministic and randomized query complexity. And this is the AND OR tree. So here is how the AND OR tree looks on 16 input bits. It's a complete binary tree of depth 4, alternating layers of gates. Each layer has like ORs and ANDs alternating. And the evaluation of this tree on a particular input it's sort of clear. Right? You just percolate up and out. Sachs and Wigderson, so its deterministic query complexity is easy to show that it's maximal. Sachs and Wigderson showed in the mid-80s, that its randomized query complexity is polynomially smaller than its deterministic query complexity. And what we show in our work is that the rank of this function is close to the deterministic query complexity. In fact, it's equal to n plus 2 over 3. So here I'm assuming that we start with an even depth and or tree. And the way we prove this is via the prover-delayer game characterization. So we show that no matter what the prover strategy is, there exists a delayer strategy such that the delayer can score at least n plus 2 over 3 points. So this shows that the rank is at least n plus 2 by 3. And for the other side, we say that no matter what the delayer strategy is, there exists a prover strategy that only allows the delayer to score at most n plus 2 by 3. So this shows an upper bound on the rank. Yeah. And this happens to take up a lot of space in the paper and a lot of case analysis and all. I invite you to read the paper. Read it. Okay, so are there questions about this part?
Hi, sir. Stupid question. So this is finding the rank, but some of the title was rank versus randomized rank. So is it a randomized rank also?
Sorry, I didn't mention that. A good question. So the rank is maximal, and again, as I alluded to on the previous slide, randomized rank is at most randomized query complexity. I'm just going to use this simple form.
Okay.
So the randomized query complexity, because of Sachs and Wigderson, is polynomially small. So this shows a polynomial separation between rank and randomized. Yeah, thanks.
What's the lower bound on the rank?
That we don't know.
From this particular.
We don't know.
So it's unclear if
It's unclear if this is actually right. Yeah.
that bound being for the randomized rank.
No, so what is the best bound of the randomized rank for this?
So the best lower bound I know is just this.
Upper bound.
The best lower bound.
Yeah. So I don't know of a lower bound that's smaller than n to the 0.753.
No. The lower bound of the randomized rank.
Sorry. Oh, okay. So sorry. Yeah, I don't know. Okay, we our main motivation was to separate rank and randomized rank, so we didn't think of.
No, but that would give you. I mean, so you're saying what I'm saying is like it is possible that for example, the randomized rank is log of it.
For all I know, I suspect not, but
But you know.
no. I mean, I would suspect that for this function, it's still poly n.
How is the separation? Why is the separation now between rank and randomized? Because randomized rank.
Randomized rank is at most randomized query complexity.
Oh, I have that's right. So it's that kind of it's a difference between n and.
Yeah, but I don't know what the randomized rank actually is. Potentially log n constant or something, but I suspect it's poly n.
Is there a prover-delayer game characterization for randomized rank as well?
So I'm not so sure about that. Like even for example, query complexity can be phrased as a game, like where points are scored when variables are answered. I don't know what the analogous game is for randomized query complexity. Also, this randomized rank is a measure that we define in this work. So we haven't seen it used anywhere. Any other questions? So if I lost you people or if you lost me, I welcome you back to the third part of the talk where I'm going to talk about upper bounds on quantum query complexity. So if you have classical query algorithms for Boolean functions, or classical decision trees that have nice structure. I'm going to tell you how to extract from it quantum query algorithms with potentially some speed up. And then I'll show you where these measures of rank and randomized rank enter the picture. So if you want to show an upper bound on the quantum query complexity of a function, one way to do this is you just tell me a sequence of unitaries along with oracle operations and tell me that this is the algorithm, and then you prove to me that this algorithm is going to be correct. But this typically is a hard task, which is this one. But then there are known results that say that you can give me easier objects, easier to analyze objects that imply upper bounds on the quantum query complexity. And two such objects are a dual adversary bound and a span program, which I'll define on the. I won't define it formally, but I'll tell you a little bit about them on the next slide. So here is what again a circuit looks like that depicts a quantum query algorithm. So in the mid 2000s, Hoyer, Lee, and Spallet defined a quantity which is maximization of a certain semi-definite program. So they defined this quantity called the adversary bound and showed that quantum query complexity is at least omega of the adversary bound, is at least as large as the adversary bound. And subsequently, it was shown that the dual of this program, which is a minimization semi-definite program, actually gives an upper bound in the quantum query complexity of the function. So you can actually take a witness to this minimization and convert it into a quantum query algorithm.
Doesn't this imply the quantum query complexity is exactly the objective value of the SPP?
Theta, yeah. I think so. Yeah, that's right.
So why theta, why not exactly? Because one and side are equal.
Yeah, this is all up to constants here. So you lose a constant in this construction over here. And I'm not sure about this one, but I suspect that there's a constant hiding in this omega. But then okay, so this is the dual adversary bound. So it's now in the last decade or so, this is one of the techniques that's been used widely to give quantum query upper bounds. You give a solution to this minimization SDP, and by this result here, that yields a quantum query algorithm for your function. And another mathematical object that's been used to give quantum query upper bounds are span programs. These were first introduced in classical complexity theory in the context, I think, of log space complexity by Kasper and Victorson. And in 2011, it was shown that even span programs characterize quantum query complexity of Boolean functions. Span programs have a certain complexity measure associated with it, which I'm not going to define now. And neither am I going to define the adversary bound, but it is on the next slide in case at the end of the talk anyone wants to see it. It's here. All right. So now let me tell you about these pair of works of Beigi and Taghavi from 2019 and 2020, some recent works. In 2019, Beigi and Taghavi defined a variant of span programs that shows upper bounds on the quantum query complexity of relations. If you're not comfortable with relations or partial Boolean functions, just replace this whole object by f, a Boolean function from 0,1 to the n to 0,1 for the rest of the talk. And just trust me when I say that relations are generalizations of Boolean functions. So here is what they showed. So whenever I write relation, I might say a Boolean function. So they showed that if you have a decision tree, remember equivalently a quantum query algorithm that computes a Boolean function f, then its quantum query complexity is at most square root of its depth times its guessing complexity. Now, you might note that I have this tilde here. This is intentional. So given a function f, what is f tilde? It depends on the tree here. And f tilde actually outputs the leaf of t reached. So f tilde takes as input a string x, and it outputs which leaf of t was reached on that input x. So again, the depth of T is just simply its the classical query complexity of that algorithm. So potentially the guessing complexity could be order 1, for example, in which case this gives you a quadratic saving. So if you had a classical query algorithm, let's say of cost k, of depth k, and guessing complexity order 1, this would give you a quantum query algorithm of cost order square root of k. And how do they show this? It's via constructions of these modified span programs and also constructions of adversary solutions, which are very similar constructions. And what do? They say, let's look at this query algorithm in the form of a decision tree, assign real weights to edges of this decision tree, and based on these real weights, they obtain a span program and also a dual adversary solution, each of which has complexity, some certain function of these weights, and then they instantiate these weights, and the bound that comes out is exactly this. It's a very high level sketch of what they do. Yeah.
So F is a subset of L to the power n cross n.
Yes.
So on a particular input X, which is in L to the power n, you are free to output any of the things
Yes.
that it comes with.
Yeah.
But potentially this is also partial.
Yeah. So there could be inputs in L power n that have no matching partner. Yeah. Yeah. So this is a generalization of, yeah, I'm talking about true relations, I guess. Yeah. So I'm not lying when I say subset equal to L to the n cross n. That's just. So F tilde is, I've hidden some dependence on T here, but so F tilde is, so given F, just think of F as a Boolean function now, and given a tree computing it, F tilde takes as input X. So imagine running T on the input X, you'll reach a certain leaf. So F tilde is the function that tells you that leaf.
The identity.
Not just the value at that leaf, yeah, the identity of that leaf.
The quantum algorithm solve in a hardware problem.
Yeah, exactly.
So simulating.
Yeah, it's sort of simulating the tree in sums.
But it is the identity of the leaf, but not the value stored.
No, so it's more general.
Yeah. So basically, it is Q of T. F is gone away.
Sure, Q of T, sure.
Q of X sub T.
F sub T.
Yeah, so that's F sub T is what I've defined as F tilde.
But T is hidden.
Yes, T is hidden. So F sub T is probably a more accurate notation, you're right.
Radha is asking if the quantum query bound is equivalent to negative weight adversary method. So are you losing something by just using positive weight?
No, so whenever I talk about adversary method, I am talking about the negative weight adversary method. I'm not talking about the positive weight adversary method. Wait.
Should I just get rid of the top part?
Oh, yeah. So that's why I specifically said the word general here. I mean, the positive weight adversary method has been known for much before this. Thank you. Any more questions? This part? Okay. I will.
10 minutes.
So I hope this sketch at least gives you some information of how Beigi and Taghavi proved this result. So what one of our contributions is, so they ask, can you use different assignments to the weights and obtain better upper bounds, because their upper bounds were given by a specific instantiation of the weights, and we're going to answer this in the positive, but for that I need a little bit of definition. So I mentioned earlier that a path is, when I say path, I'm going to mean a root to leaf path in a tree. And now I'm also going to define the set of edges given by P bar, which are edges that touch this path in exactly one vertex. For example, here, the blue edges form a path P, and the red edges are those incident on exactly one vertex in this path. So the red edges are P bar for the blue edges. So what we show is basically by staring at Beigi and Taghavi's proof and picking it apart, we simplified their adversary bound construction a little bit, and then we also observed the following, that the upper bounds that they obtain on their dual adversary bound and the span program complexity are actually captured by this optimization program here. Roughly speaking, what is this optimization program? You are asked to assign real weights to the edges of a decision tree, which is given, and you want to minimize the sum of weights along neighboring edges of a path. So for all paths, you want the following: you want to minimize the sum of weights along neighboring edges of that path, and you also want to minimize, you want the sum of inverses of weights on that path to be small. So if you go back to this picture, that would mean you want 1 by this weight plus 1 by this weight plus 1 by this weight plus 1 by this weight to be small. Moreover, you want this weight plus this weight plus this weight plus this weight to be small. There's some sort of trade-off in inverses, actual variables. This is a polynomial optimization program, and what we show is that this optimum value has this neat recursive form, reasonably neat recursive form. And to show an upper bound on this, we actually construct these weights from the bottom up, from the leaves up. I'll give you an example of this on the next slide. And for the lower bound, it's much harder to describe, but given a weight assignment to a tree T, this induces a weight assignment on the left subtree and right subtree. Now, based on these weight assignments, we define some values v1, v2, v3, v4 such that opt can be written as this quantity, and the maximum of two values is at least as large as any convex combination of them. And then our choices of v1, v2, v3, v4, and delta are such that magically whatever comes on this right hand side here equals this quantity over here. So we show that opt actually equals this recursive formula over here. So here are two examples. So if we consider the AND function on 3 input bits, so the red edges correspond to the outputs of those queries being 0, and the labels of the edges are the weights assigned in the optimum solution, the optimum solution. The eventual quantum query upper bound, or the dual adversary bound and the span program complexity, and hence the quantum query complexity, is going to be bounded above by opt. So for the parity function, we know that its quantum query complexity is maximal up to a factor of 2, and that's captured here. And for the AND function, the optimum value we attain is this symbol, which is defined here. And the choice of notation phi is not coincidental. Okay, so it's not clear, at least to me immediately, why this value, if you extend this to a depth n tree, is square root of n. So we know that the quantum query complexity of AND is square root of n, but we eventually show that this is bounded from above by square root of n, because we show that the opt value is at most the square root of the number of nodes in the decision tree. And Beigi and Taghavi showed by their specific weight instantiation that the quantum query complexity, or the opt value, is order square root of rank times depth, or the guessing complexity times depth. And this size bound was known only for Boolean functions, whereas our bound applies for relations. Technically speaking, the size bound was in terms of formula size, but then we observed that formula size is at most decision tree size of the constants. Now, if you look at these two bounds, you might say that, oh, okay, decision tree size is typically some very large number. And is it ever going to give any useful bounds? Any bounds that are more useful than this first bound? So in fact, if you're willing to tolerate log factors, then it doesn't give more useful bounds. But if you are not willing to tolerate log factors, as is the case with me, if you've been following my work over the last few years, I don't tolerate log factors. Then we actually show trees for which this inequality is tight, in the sense that this bound that we prove is strictly stronger than the rank depth bound due to Beigi and Taghavi. So here's a quick summary of what I spoke about today. So we first saw that this notion of guessing complexity introduced by Lin and Beigi and Taghavi to prove quantum query upper bounds in terms of classical complexity. Classical query upper bounds. This notion of guessing complexity actually equals rank. We showed a separation between a polynomial separation between rank and randomized rank for a total Boolean function, which was the complete binary AND OR tree. Then we observed that this Beigi and Taghavi construction gave quantum query upper bounds in terms of the optimum value of a particular optimization program, to which we provided a recursive solution to the optimum. And we showed that that recursive solution is bounded from above by order square root of decision tree size of the underlying classical decision tree. And Beigi Taghavi's construction shows that it's at most square root of rank times depth. Now, what I haven't told you is that these same techniques also give you results like this. So quantum query complexity of F is at most randomized rank of T times randomized depth of T, where T is a randomized decision tree computing. So this is another reason why I brought up randomized rank earlier. So, and it's also at most order of square root of randomized decision tree size of F, defined just defined naturally as the randomized analog of decision tree size. So now just plugging in this randomized rank times randomized depth upper bound for the AND OR tree, we know from this result of Sachs and Wigderson that the randomized depth is at most n to the 0.753, and it's randomized rank, we don't know of a better upper bound than that. So this gives you a quantum query complexity of the AND OR tree to be at most order n to the 0.753. But we do know for a fact that this function actually has quantum query complexity order root n. So can we show a better upper bound on, for example, on the randomized rank, optimum value for a specific decision tree computing this AND OR tree, is it small? It's not clear to me at least.
So there are tight upper bounds from the quantum query complexity of AND OR tree. No? There are lower bounds.
Both. So it's known to be theta square root of it.
Doesn't that now give you a lower bound on the randomized rank? On the AND OR decision tree.
So
Well, because you just said that you could replace that rank by randomized rank.
yeah, so you can replace this by randomized rank and randomized depth here.
Yeah, but now you know that so that would be the an upper bound on the quantum query.
That's right.
Right?
That's
So
right.
you have a lower bound. So if you just combine the two, you don't give you some lower bound on the randomized rank.
I think you're right. I think you're right. Thanks. Sorry.
I don't know.
So I think if you plug in like randomized rank, randomized depth, and then we know that this cannot be smaller than root n.
Yeah.
Yeah. Yeah.
Maybe we can work it out after. So another interesting question is, are rank and randomized rank polynomially related for all total functions? So this is known to be true in the analogous query complexity question. And that's it. Thank you for your attention.
Don't have a question, but this rank of Sachs and linear, we consider the following operation on the tree. You start from any tree and its leaf captures all its ancestors for which it is the only leaf. Okay. If you want, you can draw it and make it.
Sure.
So you can draw your own tree, your favorite tree.
Is there an opening? I'll draw a tree if I can find something. So before that, let me quickly say that there are other analogous notions of rank. There's another very cute one that's you consider a decision tree, and rank is equal to the maximum depth of a complete binary subtree inside it, up to edge contractions.
A binary tree.
No, some of them are not.
Initially, first step, yeah. So first step, you will just erase the leaves. Yeah, and the edge that connects them.
Oh, okay.
Also the edge, yeah, definitely. Definitely. Yes, those. One more, yeah. Next time again, do the same thing. And the other leaf also takes. Now, the bottom leaf, it just
As one
completely takes everything off.
Nice.
Okay. So how many steps does it take for the tree to vanish?
Right. This sounds like another characterization of rank to me.
I think it is similar to contraction because those two edges have got contracted into a single one and then they vanish together.
Probably, yeah, that sounds right.
So this appears in some paper of linear analysis.
Thanks. So,
So, but what is the relationship of this rank and
This is the same.
same rank?
Yeah. So that was defined recursively bottom up,
Oh,
by top down. And this I'm just giving you a bottom up algorithm which gives how many steps does it take for the tree to vanish. But not just deleting the leaf and everybody for whom you are the sole descendant. Yeah. So this particular leaf right now is the only descendant for all its ancestors. So they all go. What?
yeah, so rank also gives you lower bounds on decision tree size, which is studied in proof complexity. So, for example, rank lower bounds imply size lower bounds for tree-like resolution proofs. Yes, they also they can be converted into algorithms, and both of the works that I mentioned actually construct algorithms. So yeah, so they actually give you a sequence of operations that you apply this, and this is an algorithm for computing function. Bounded error. This is all bounded error quantum variable.